see. Fine. Is it on? Let's start today, everyone. So let's continue our functional analysis 2019. I hope this has been a good experience for you as it has been for me so far. So this is lecture 15, right? And today I want to discuss with you a little bit about, come back to the discussion on LP spaces. Right, we're going to discuss LP spaces from the point of view of reflexivity and separability, let's say. Okay, this is now mostly, we'll be discussing now chapter 4 of quizzes. There is part of the discussion in chapter 4 of the book that we already did in the beginning of the course, okay? So, in principle, well, the basic definitions of LP spaces we already did, right? So we defined what the LP space is. We proved the basic properties, right? We proved Holder's inequality. We proved Minkowski's inequality. So we essentially proved, well, Holder's inequality, Minkowski's inequality, which is the same as, in this context, the triangle inequality. And we ended up proving that this is a Banach space, right? These guys are Banach spaces. I guess most of what we have discussed, we did in the context of RD. So, most of we discussed. Mostly, let's say, we discussed LP of, say, RD. But, well, most of the properties that we discussed for LP of RD, they hold true for LP of any other measure space, okay? So, well, for practical applications, say if you're in analysis or PDEs, you will eventually just work with LP of RD or subdomains of RD, but you can be working on other manifolds, probability spaces. So maybe let's just put the discussion into a general framework. So let's see, and I will just see when we have to go back to RD or not. So I suppose you are all familiar with the notions of measure and integration, right, on a measure space. So here, so let me just recall this basic setup. And the setup would be like, this is, we're going to call omega. This will be a measure space. Okay, so the space M, let's say M would be the sigma algebra of measurable sets, right? The sigma algebra of measurable sets has essentially few properties. It's a non-empty thing, so let's just put the empty set and the whole empty set belongs to the sigma algebra. What else? If A belongs to the sigma algebra, then A complement belongs to the sigma algebra, and then if AI belongs to the sigma algebra, then the countable union of AI belongs to the sigma algebra. So it's just sigma algebra is essentially just a collection of subsets to satisfy these three properties. If you want, you can replace the first property by just saying that the collection is a non-empty collection. Because then for any set, you have the complement. If you have countable unions, you will have also countable intersections. Then the intersection of these two, A and A complement, will be the empty set will be there. Okay? So this is just a collection of any collection of sets that satisfies these three properties we call sigma algebra, and these we call, say, measurable sets. So to measure the space. And then you have your measure. Your measure, let's call it just mu, and it just satisfies one property. Your measure has to satisfy what? That the measure of the union of some sets AI. Okay, so this will measure. First of all, this is a measure on the measurable sets. Okay, we will only measure the measurable sets, satisfying the mu of a certain union is just the sum of mu of when the AIs are pairwise disjoint. Okay, so this is essentially a crash course in measure theory. You'll learn these three ingredients: your measure space, your measurable sets, and your measure mu. Right? It has just to be it's a non-negative function, obviously bigger or equal than 0 always, and it's what we call sigma additive. It adds up. The measure of the whole thing is the sum of the measures of the pieces if the pieces are all disjoint. I suppose you're familiar with this from the Rio analysis course that you took in the first semester, right? Am I correct? Did you end up defining the Lebesgue measure in this class or no? Yes. So you define the exterior measure, and so one thing is to actually, define what the measurable sets are. So it's very beautiful construction on RD to define the Lebesgue measurable sets. This was essentially what I was covering last week with the students in Pakistan that I visited. So it's a bit fresh.
Was it taped or not?
Huh?
Was it taped? Recorded?
No, it was not recorded. Well, maybe it was, but just for internal purposes. I'm not sure it's online. Anyway, so we usually assume that my space, my sigma, is a sigma finite space. So it's what we call sigma finite space. Meaning that your omega can be written as a union of omega n's, where the measure of each omega n is actually less than infinity. Okay? Remember, this measure mu here in principle, measure mu of A, is a number which is bigger or equal than 0, and it's less than or equal to infinity. It could be infinity, no problem. Okay. So once you have a measure space, a sigma algebra, and a measure on the sigma algebra, you can talk about integration, and you can talk about the LP functions, okay, of this whole structure. Okay. If you don't remember measure theory very much, so LP of omega for us will just be the spaces of functions f, say, from omega to R or C that are measurable functions. And measurable means that the preimage of, say, measurable sets on the real line is measurable in this sense, if you want. Measurable functions with the so-called LP norm, is the integral of absolute value of f mu in omega to p over p, this thing finite. Okay? So it's okay for our purposes today if you just want to think about RD and LP of RD or LP of subdomains of RD, that's okay. But if you want all the things that we're going to discuss goes a little bit beyond from LP of general measure spaces. Okay? In particular, the spaces that I want to draw your attention, at least at this moment, so are the spaces of, so the very basic examples, okay, that I want you to have in mind are, of course, spaces LP of RD, or LP of subdomains of RD, okay? So if you are in the real line, LP of the 0, 1, for example. Okay? This is, of course, when P is less than infinity, and when P is infinity is the essential supreme. So this are the examples that you want to have in mind. And another source of nice examples are the spaces which we call little LPs. Okay, little LPs, which is essentially this construction, the LP space of the natural numbers with the measure, with the so-called counting measure. Okay? This little LP is nothing more than the space of sequences, say, X, which are just sequences of real numbers, such that the norm P of X is just the sum of xi to the P, 1 to infinity to 1 over P, that's fine. Okay. This is essentially having your omega as being the natural numbers and assigning for each natural number. If you have a subset, well, the sigma algebra will be all the subsets of the natural numbers, and the measure of a subset of the natural numbers is just the amount, how many elements that subset has. Okay? So once you have these three elements, the natural numbers, all the subsets, and the counting measure, and you do the LP of this, in this sense, this is just space of sequences where you get out. This is just integration. So everything is under the one whole framework, but these are just the spaces that I wanted to have focus your attention. LP of subdomains of RD, or spaces of sequences. Okay? So as we proved for RD, all of these guys are Banach spaces. Okay? They are Banach spaces. They are Banach spaces. We have Holder's inequality, we have the triangle inequality, and we have that they are complete. Okay? I will not prove this again. Well, the same proof that goes for Rn goes for this, for Holder's inequality and Minkowski's. I draw your attention for this property of being sigma finite. In RD, this is absolutely obvious. You can just fill in your whole space with cubes. But some of our proofs that we're going to do today actually decompose the spaces in some things with finite measure. Let's say, are we good? Good. Okay. So, let's see.
We might assume that these segments to be disjoint, right?
Not necessarily. Okay. So, for example, in RD, you can take cubes that contain each other. Just a sequence of increasing cubes that fill in the space. And so for some of the arguments, you get your function, you truncate it, multiply by the characteristic of the cube, and then you send n to infinity. So it doesn't have to be disjoint. Of course, if you wanted to make it disjoint, you can, of course, just take, if I give you this family omega n's, you can just take omega, you can take another family when you get omega 1, and then the second guy would be omega 2 minus omega 1, third guy would be omega 3 minus the union of the previous guys. So from every family you can construct a similar family, but disjoint, guys. It's up to you. Okay, good. So now let's discuss. I want to give some more concrete examples of the theory that we have been studying over the past weeks. So we have talked about general Banach spaces, weak topologies, and when they are reflexive, when they are separable, blah, 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 blah. But now let's start to give some example, and let's start deciding when some spaces are or not reflexive, who are the duals of these guys, like to give concrete representations. Okay, so the first theorem, so that I want to prove to you today, and let's call it the Riesz representation theorem. want to write it in the following way. Let's see. LP is reflexive if 1 is less than P less than infinity. If phi is a guy in the dual of LP, then there is a unique U belonging to LP prime such that phi acting on F is equal to the integral of U F for every F in LP. And moreover, norm of U in LP prime is actually the norm of phi in LP dual. So we mark from now on, we identify So this is a very, 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 very nice theorem. Okay? So first is the case P not being an endpoint. So I'm not going to write LP of omega, and I'm not going to write integral of omega, d mu, where mu is a measure, but whenever I don't write, you may assume that this is a general statement for the class of all sorts of measure spaces that I have been discussing here. So what I'm trying to say is that if you are not in the endpoints, 1 and infinity, then LP is a reflexive space. Okay. Then, this is one part of the theorem. The other part is to actually characterize what's the dual. So in fact, if phi is a guy in the dual of LP, is a linear functional in LP, then there is a unique function U in LP prime, the conjugate exponent, and recall always 1 over P plus 1 over P prime is 1, so this is the conjugate exponent, such that phi acting on F is actually the integral of U against F. So all the functionals can be represented by integrals of F against the function U in LP prime. And moreover, the norm of U in LP prime is actually the norm of the function of phi in the dual space. So from now on, we may actually identify this dual space of LP with the space LP prime. Okay? And as a matter of fact, from this statement, if suppose you don't know this is reflexive, if you just had the Riesz representation theorem, if you know that the LP prime is actually LP dual is LP prime, you apply the dual again, and the dual of LP prime will come back to LP. Hence, this will show that it's reflexive. So, in some books, when you read about this, some books, especially in real analysis, that they haven't talked about functional analysis before, they haven't talked about what's dual, what's reflexive, and so on. They might not have this, and they might prove this directly. Every continuous linear function on an LP is a function on LP prime. Therefore, it's a reflexive. We'll go a little bit of a different way here. Riesz does a little bit different. Proves that it's reflexive first, and then this will follow very easily. Good. So very nice. So this is a concrete example. So from now on, if you are not in 1 or infinity, the dual of LP is LP prime. Let's do a little bit of.
We are assuming that we are having the sigma finite measure.
We're always going to assume that we have a sigma finite measure. Yes. Okay. So it's part of the setup that I wrote here. Measure space, the measurable sets, the measure, and the measure is sigma finite. We will see when it's needed. Okay, good. Let's see. Okay, so let's try to prove this. Let's discuss and how would we start by proving this. So suppose I want to prove that a certain space is reflexive. Well, in the previous class, we took a long time to prove a very deep result on how to prove that something is reflexive. So let's try to capitalize on that and use it to justify saying, okay, so here you see, this is why the...
One question about it, just we know the LP, we have to prove LP star is LP prime, but it's like LP star is isomorphic to LP prime,
Yeah.
or just equal?
If you want, isomorphic. Isometrically isomorphic. Okay?
When we are solving some problems, we can write just LP star is LP prime, or we have to write, do we need to write something about LP star is just isomorphic to LP prime?
Just consider them equal, that's fine. But have it in mind that it's isometrically isomorphic. So you see, it depends on the context that you're working. Okay, so you gotta be a little bit careful sometimes. Like if you have a space of sequences in L2, for example, and you consider the operator T that maps a sequence in L2, say A1, A2, blah, 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 and to the sequences. So T of a sequence, T of this guy will just be a sequence, say 0, and then A1, A2. It's just a shift to the right. Okay? So of course you can say that T of L2 is isometrically isomorphic to L2 itself. By just taking anybody, so there is a isometric isomorphism between T of L2 and L2, right? T of L2 will always have 0 in the first entry, so the isomorphism will just say delete the 0 and consider this sequence. This is an isometric isomorphism, right? But on the other hand, T of L2 is contained in L2 and it's different, right? So be careful in the context that you're working on. So if something is isometrically isomorphic to somebody, it means that there is an isomorphism, which is isometric, but it doesn't necessarily mean that it is equal as sets. Okay. Okay. So So I hope it will be clear from the context what I mean, right? So every function here in LP prime gives by the integration an element in the dual of LP, and conversely, every guy in the dual of LP can be written as an integral against a certain function. But let's see, when we get there, we'll formalize this isomorphism there. So I want to prove that a certain space is reflexive, and I want to use the uniform convexity. Okay? So let us show that LP is reflexive for first case 2 less than or equal than P less than infinity using the uniform convexity. Okay, so this is, let us divide in these two cases. So the first case, case 1, is actually this case here. So my P was going to be between 2 and infinity. Okay, and then the equality that I propose to you that we use is this one. Let's see if we can prove this. So let us prove that I want to propose to you that we prove this inequality. Okay? Where your f and g's are functions in LP. prove this, okay, so if we prove this, this implies that LP is uniformly convex, and hence reflexive, right? Because if, say, F is less than or equal than 1, G is less than or equal than 1, the LP norm, and F minus G is bigger or equal than epsilon, this means that F plus G over 2, P norms, if I just move this guy to the other side, what I get is less than or equal than 1/2 of 1 plus 1, so I get 1. And I get here minus, this is bigger than epsilon, so this is less than epsilon over 2 raised to the p. All right? So, yeah, what I wanted is that, remember, so this implies that F plus G over 2 P norm is less than or equal to 1 minus delta, if you want, 4 delta equals to, so let's see, maybe 1 minus this thing. I just have a P raised to the P powers here. So the only thing we care is that F plus G over 2 is less than 1 minus something. Okay? So I'm just writing here, so, okay, so this is less than 1 minus delta for this delta in this thing. Am I correct in writing this? Maybe.
I think there should be
Maybe
divided by B,
Maybe this. Okay.
but I think it should be multiplied by B, or 1 over B.
This is 1 minus delta, so when I take this delta here, 1 minus this thing, so 1 minus this one, just get this thing. Then I raise both sides to the P power, I get to the P, and then 1 minus epsilon. This is okay. Right, okay, good. So, again, if this is in the unit ball, this is the unit ball, and this is bigger than epsilon, then there's some delta, which depends on epsilon, of course, so that this is less than 1 minus delta. This is uniform convexity, and implies that it is reflexive by the result. Okay, so we're using this theorem of Newman-Pettis that we proved in the last class. Good. So all that we have to prove is this inequality here for the LP norms. Okay? This is no rocket science. It's just basic calculus. As a matter of fact, let's just prove that this inequality here. So when I take the LP norm raised to the P power, so I eliminate the factor 1 over P out of the norm. So this is just an inequality between some integrals. I just have to prove that it holds pointwise. So we just need to prove that it holds pointwise for each value of f of x plus g of x. Then I just sum, right? Okay, so I just now have to prove that it holds pointwise the following thing. Remember, so this first guy is just the integral of what? F plus g over 2, right? Raised to the p. The second one is the integral of f minus g over 2, raised to the p. Less than or equal than 1/2 integral of f to the p plus integral of g to the p. So this is what this inequality means. So I want to prove that in the integral this inequality holds. I'm actually going to prove something stronger. I'm going to prove that for every point x in the domain omega, this holds for f of x and g of x. So it is sufficient to just prove that, let's say, we just want to prove that a plus b over 2 to the p plus a minus b over 2 to the p is less than or equal than 1/2 a to the p plus b. This is the inequality that I want to propose that we prove pointwise for any A and B real numbers. Yeah. A and B real numbers. Let's see if we can prove that. How would we prove such a thing? Well, maybe different ways to prove. So let's just, let me just call.
We can all call AT and define a function.
Yeah, we're gonna do this anyway. So let me just shift things a little bit here. Let me call alpha a plus b over 2 and beta a minus b over 2. So what I need to prove is that, say, alpha to the p plus beta to the p is less than or equal than 1/2 of, and then a just becomes what? Alpha plus beta to the p, and then b is just alpha minus beta to the p. Okay, this is what I have. Let's try to prove this. I may change here freely, so if I change alpha between alpha and minus alpha and beta to minus beta, I can just do that, and so therefore I may assume that, say, alpha and beta are positive, right? So I can just change alpha by minus alpha, beta by minus beta, so I can assume that both of them are positive. Is that correct?
But what if I change one of them but leave the other?
Yeah, this doesn't change the inequality. So if you just change beta by minus beta, this is the same, and this flips with this. Okay? So if you change, so that for all the 4 possibilities that you put here, alpha minus alpha, beta minus beta, the inequality that you have to prove is the same. Okay? So I may assume that I'm working with positive, non-negative numbers. And since this is, of course, symmetric in alpha and beta, I can also assume that, let's just say that beta is less than or equal than alpha. Let's just say that. Okay? So let's construct a function now. So let us fix beta bigger than 0 and consider the function as a function of f of x just being what the right hand side is. It's just 1/2 of, let's say, x plus beta to the p plus x minus beta to the p minus, so this minus x to the p minus beta to the p. So I'm going to consider this function for x bigger or equal than beta. So I want to show that this function f of x for x bigger or equal than beta is bigger or equal than 0. This is what I want to show. In particular, when I plug in x equals alpha, this will be bigger or equal than 0. Okay? Okay, so there's no big deal. This is my function, so I just have to see how much is the f of beta. So if I just put x equals beta here, I get what? I get just 2 beta to the p power. So I get 2 to the p minus 1 beta to the p, because I divide by 2, minus, and then here, beta to the p minus beta to the p minus 2 beta to the p. So what I get is beta to the p and then 2 to the p minus 1 minus 2. And since I am on this range, since I'm assuming that p is bigger or equal than 2, this is going to be bigger or equal than 0. Okay, so the point that I'm starting, f of beta is bigger or equal than 0, and what I have to check is just the derivative is positive. So if I prove that the derivative is positive, I start bigger or equal than 0 and I go up. So the derivative of this function as a function of x is what? So let's just say this is p over 2, and then x plus beta to the p minus 1 plus x minus beta p minus 1 minus p x to the p minus 1. Right? So if I just but put p outside here, just put p outside here, it's going to be divided by 2. It's just going to be p times this guy. And this is bigger or equal than 0 because the function, there's a function here, y to the p minus 1 is convex. Okay, so these two guys add up to x. So this is bigger or equal than 0 since the function that maps y to the p minus 1 is convex. So the value, the average of the values is bigger or equal than the f of the average. Right, this function is convex again. When you take the first derivative, you get p minus 1 to p minus 2. When you get the second derivative, is positive because p is bigger or equal than 2. Is that clear? Why this is positive? Okay, good. So then we're fine, right? So I'm just evaluating this expression for x bigger or equal than beta. The value of f at beta is bigger or equal than 0, and the value of the derivative is non-negative. Therefore, f of alpha, which is the quantity I'm aiming for, is non-negative. Okay. So this concludes the proof in this case. Are we fine? Good. Now, let's do the proof in the other case. In the case when p is between 1 and 2. There is a similar inequality that we can prove along these lines. So these are called Clarkson inequalities, if you want. There is a similar inequality that we can prove, but we don't have to go through the calculus machinery again. We can try to use some of the things that we have learned in functional analysis, some of the nice arguments. So let's do it differently. And the reason is the following. Good. Second case, and this is the case 2 less than or equal to p less than infinity. Okay, how are we going to do it? And here's the moment to draw our weapons.
Sorry, this was the first case.
Oh, thank you. One less than p less than or equal to less than 2. This is what's missing, right? Okay, so let's do the following thing first. Before we do this case, let's try to do now. Let's try to construct the isomorphism between the dual of LP and LP prime. So let's see how we should do it. Now, generally, for 1 less than p less than infinity, okay, there is a map which we're going to call T that goes from LP prime to the dual of LP. And the map is very simple. I am going to get a function u here in LP prime, and I'm going to assign a functional in LP. And the function will be integral. I'm going to say that T of u is going to be a function, a guy, this guy, and I have to tell you how it acts on a function in LP. T of u acting on f will be just the integral of u times f. Okay? So we just constructed this map that assigns a function u in LP to a functional tu in the dual of LP. Tu acting on a function f is just integral of u against f for any f in LP. So the map that this map defined like this, it's obviously linear. If you take two u1 and u2, you see that they will just add up here. Again, this is just a real number. So this is linear. If you multiply by lambda, you just multiply by lambda here. So this is linear. In fact, by Holder's inequality, what you get is that Tu of f, Tu acting on f, which is just the integral of u against f, is less than or equal than u in LP prime times f in LP, right? So if Tu acting on any function f loses to a certain number times the norm of f, this means that the norm of T of u as an operator, as a guy in LP dual, has to be less than or equal than this quantity here. Do you agree? Okay, again, the norm of this guy as an element on the dual space is just the supremum of this when the norm of f is 1, right? So if the norm of f is 1, you would get that it's less than or equal than this guy, so it's less than or equal than this quantity. So this makes this map that we created here is actually a bounded map. It's linear and a bounded map. The norm on this side loses to the norm on this side. Okay, so this map is linear and therefore continuous. Bounded, right? Okay. Are we good? Good. Now, let's see. I want to show that it actually preserves the norm. So I want to show not only that the norm of T of u in LP dual is actually less than or equal than this, but I want to show that it's actually equal.
There is equality case for Holder's inequality.
Exactly. So we just use the equality case. So in fact, right? So we know how to make the equality in Holder's inequality, right? So by choosing f to be equal to, let's say, maybe I should put u to a certain, so morally speaking, I want to choose f to be u to the, u belongs to LP prime. It's going to be just like p prime minus 1. This is what I want to choose, right? But then I want to align, so all my functions are real valued. So what I want to do is u to the p prime minus 2 times u. This is what I want to do, just to make sure that I have a u squared here, which is non-negative. So this function here, u to the p prime minus 2 times u, of course, p prime minus 2 might be below 2. I don't care. So this is just when u is different from 0. Okay, so when u is 0, f is 0. So let's just define f to be absolute value of u raised to this power times u when u is not 0, or 0 when u is 0. So this function here verifies the following properties. First, I claim to you that this f belongs to LP. In fact, the integral of f LP is just the integral of absolute value of u p prime minus 1 raised to the p, which I believe is,
shouldn't it be b dash b prime minus 2?
p prime minus 2, that's here. So I claim that f belongs to LP.
Yes.
So let's just compute what the norm of f LP is. is just u p prime minus 1, because I have the modulus of absolute value of f would have another u here. This is times u, okay? This times u. This would be this raised to the 1 over p. But how much is this thing inside here? So 1 over p plus 1 over p prime is 1. So this means that 1 over p prime is 1 minus 1 over p, which is p minus 1 over p. So p prime is p over p minus 1. Okay? And if I reverse the rows, I get also that p is also p prime over p prime minus 1. So if I have here p times p prime minus 1, so p times p prime minus 1 is certainly just equal to p prime. So this is just the integral of u to the p prime raised to the 1 over p. Okay. Well, that's okay. So this shows that this function belongs to LP, right? And this is, so okay, so let's just say that the LP norm of f is equal to the LP prime norm of u raised to p prime over p. Is that correct? Okay, good. Now, if I take this function f and apply it to my functional, so I get t of u, comma f, okay, is equal to, this is always, remember, always less than or equal than the LP norm to the dual times the norm of f. This is equal to the integral of u times f. Integral of u times f here is just the integral of u to the p power. Are we okay? Because f is u to the p prime power. P prime minus 2 u times u. Okay? Then I'm okay. So this is equal to norm of u p prime raised to p prime. Therefore, this change of inequalities, what I conclude is that norm of t of u in LP dual is bigger or equal than norm of u p prime raised to p prime divided by the norm LP of f. Norm LP of f we just calculated is just this guy here. So u p prime over p. So what is this now? P prime minus p prime over p. I claim to you that this is 1, is that correct? If I just divide by p prime, I get 1 minus 1 over p is 1 over p prime. So this is just norm of u. So I proved that the norm of t of u in LP dual is bigger or equal than the u p prime, just the reverse of this thing, by just applying in a specific, very well chosen f. Okay, so the conclusion here is that we have actually an inequality. This operator that you map is actually an isometry. Okay, so we constructed a linear operator from LP prime to the dual of LP, which is a linear, it's a continuous operator, and we actually proved that it's an isometry. If it's an isometry, it's obviously injective. We don't know yet if it is surjective, but that's okay. Now let's go back to the second case. Okay. Now let's do the second case. So we have this operator T from LP prime to the dual of LP. The image, so this is an isometry. At this point, we don't know if it is surjective, but the image of this space then is closed here. The image is closed on the other side. So if I take an isometry between, if I take something like this, T from E to F, which is preserves the norm, the image of this guy will be a closed subspace of the other side. It's a closed, if we want, it's a closed subspace of. Okay? Good. Now, I am on the regime that, okay, so let's see what I want to do. I want, let me just perhaps change the rows a little bit. So let me just change the rows a little bit between P and P prime. So let me just construct this T from P to P prime. It's the same. And then this T of LP is a closed subspace of here, of the LP prime. Just changing the rows of LP and LP prime because
But you need also to change the LB to B dash, to B prime. Because now,
is that okay? I just changed P with the P prime here. So this construction of this operator T was independent. It's just I am between just 1 and infinity. Now I want to work in this case where P between 1 and 2. Okay? I want T of LP because I want information on LP for this space. Okay, so I'm constructing this map from LP to LP prime dual. The T of LP is a closed subspace here. Since then 2 is less than or equal than P prime, less than infinity, we know that LP prime is reflexive. We have already proved. If our space is reflexive, then its dual is reflexive. We have seen this. So I am starting to use a lot of the results that we have proved. Okay? If a space is reflexive, we have already proved that if I am between 2 and infinity, LP is reflexive. Then I'm using that if the space is reflexive, the dual is reflexive. Closed subspace of a reflexive space is reflexive. So this implies that T of LP is reflexive, being a closed subspace. Okay, because it's a closed subspace. And T of LP is an isometric isomorphism with LP itself. So if it's isometric isomorphic, also preserves reflexivity. Okay, so then LP is reflexive. In this case. Okay? So this is the idea. Once you have shown the property for, say, P bigger than 2, the other case, what you do is that you construct this isometry and send it to the other side where you know things are reflexive. Well, in the dual, but space is reflexive, so is the dual. This is a nice trick to not have to do the Clarkson's inequality again. So this concludes the proof in this case as well. So now we have that LP is reflexive for any P between 1 and infinity. Great. So to finish our proof, we want to show that this isometry that we constructed is surjective. This is the conclusion of the Riesz representation theorem, that every guy in this dual of LP or LP prime, if you want, is given by T of some guy here in LP. Okay, so to conclude the proof, let us show that this map T is surjective. but this is probably also something that you have already done, right? So again, we have this map T. Forgive me that I'm changing the rows. I'm now, okay, so let's take from LP to LP prime dual and change the rows from the first construction I made, right? So takes a function U here, sends to a function T of U here, where T of U acting on F is just integral of U against F. Okay? Now, if this is the same for any F in LP prime. Now, why is this continuous? Why is this surjective? So we have already seen that T of LP is a closed subspace. We have already seen this fact.
If it has interior,
so to show that it's the whole thing, I just have to show it's dense. So we must show it is dense. How do I show that a certain subspace is dense?
Just include every non-empty open set.
every function.
Well, this is the definition of being dense.
Yeah.
But what is one way to prove an even Banach space to show that a certain subspace is dense? If I get any functional and that vanishes in this guy, then the functional must be 0. So to prove that it's dense, take any functional eta belonging to, this is my space, belonging to LP prime, dual, the dual of this guy, okay, such that eta acting on T of U is 0 for all U in LP. And we have to show that this functional eta is 0. But now, what do we know about LP prime prime? LP double.
This LB dash itself.
So we have already shown that LP prime is reflexive. So a functional eta here is given by the J of somebody in the same space, right? So since we have already proved, that LP prime is reflexive, this eta is given by the J of, say, I don't know, G, for some G on LP prime. But then, what is this condition? So then, eta acting on T of U is just J of G acting on T of U. By definition of the map J, this is just T of U acting on J. But T of U acting on J is a function of LP prime, is just the integral of U against G. And I'm saying that this is 0 for all U in LP. And I want to conclude that this G is 0. So if the integral of U, G is a function in LP prime. If the integral of U against G is 0 for all U in LP, how can I conclude that G is 0?
We can use sigma finite here to take
sine of G maybe? Using U equal sine of G?
Just take U to be one particular choice of U.
characteristic of a facet of measure of finite measure.
Look, U equals sine of G.
It was already on the board there, right? So if G is in LP prime, U can be just G P prime minus 2G. Let's take this function. So this function here belongs to LP. If G is in LP prime, this function U belongs to LP. And when you multiply, you just get the norm of G raised to the power P. If this is 0, then whatever is in the integral has to be 0. Okay, so this implies that G is identically 0, as we want. Is that clear? So again, once we have shown that the space is reflexive, to complete the proof of the Riesz representation theorem is kind of simple. We have constructed this map T that sends every function in LP to a functional in LP prime. Just have to we have shown that preserves the norm. Just have to show it's surjective. Well, if it's, let's say the image is a closed subspace, to show that a closed subspace is surjective, you just need to show that it's dense. So it's dense, you take any functional on the dual of the target space that you are, and such that when you apply to these guys in the subspace that it's 0, you have to conclude that the functional that you took in the beginning was 0 itself. Right? So we've got this functional eta. But we have already shown that this space is reflexive. So an eta in LP bidual, LP prime bidual, is just given by J of G, where G is some function in the space LP prime. But again, J of G eta applying T of U is J of G applying T of U. By definition of the J map is just T of U applying to J. T of U applying to J is just integral of U times G. So what you're saying is that the integral of U times G is 0 for all U in LP, where G is a function in LP prime. And you want to conclude that G is the 0 function. Okay? Yeah, you can do this in many ways. You said, well, I can localize and take U as with the characteristic of some sets times the signum of G of that set and prove that G is 0 in every piece. But one simple and direct way is just to take U as being the absolute value of G to P prime minus 2 times G itself. So when you plug in here, you just get the same construction that we had before. You have the modulus of G raised to the P. This is 0, so therefore G is 0. All right? Good. Many ways to do this conclusion here. No, there's no problem. Okay, so we have just concluded this very nice theorem. So from now on, this is a very, very, very nice theorem. I would put this as also one of the highlights of this course, together with the whole thing about approximations of the identity, the convergences that we have learned, the weak topology stuff, the Banach-Alaoglu theorem, the Kakutani, the fact that every bounded sequence in a reflexive space has a weakly convergent subsequence, Riesz representation theory. The dual of LP is reflexive between 1 and infinity, and the dual of LP is LP prime. Take this with you from this course, okay? Are we cool? Lots of paint, right? All right, let's move on. So we have talked about, so my goal for today's class, and perhaps the other class, is to talk about I want that we are able to decide about being reflexive or not, being separable or not for the spaces LP. And as you will see, we have to make this distinction between LP between 1 and infinity, L1 separately, and L infinity separately. So we're going to do this at each step. So we have talked about this. Good. All right. Now, how about separability? Well, separability, we have seen this before. Maybe.
State functions are these.
Say that again?
State functions are things. We proved the state functions.
Yes. Yes. Yeah. So these spaces are also separable, right? So, but then. So note the space is LP of RB, okay, for 1 less than P less than infinity, are also separable. And here I am just going to restrict myself to RD. I won't talk about LP of a huge measure space, because then I would have to talk about what is a general measure space to be separable to start with, so it gets a little bit more complicated. So let's just settle for recalling the fact that LP of RD is a separable thing. So how can you actually And here you can actually include 1 if you want. Can you guys remind me this proof? How do I show that LP of RD is also separable?
We know that we
Prove the simple functions are separable. First we prove simple functions are dense, and after that we prove simple functions are dense.
So simple functions are dense, right? Simple functions are dense.
And step functions are dense in simple.
Simple functions just linear combinations of characteristic functions of sets. And then you can do the step functions. Which are also dense. Step functions are just linear combinations of characteristic functions of rectangles or generalized cubes if you want. These are dense here, these are dense here. And then within the step functions, if you wanted to make your family countable, what do you do? What would you do?
We take rational integrants of our cubes.
Yes, so you would take, say, cubes.
We can take cubes and like maybe continuous functions. So like what polynomials?
Several ways to do this. You can take, say, rectangles with rational sides, rectangles with rational coordinates, right? So you can take here, let's say, step functions of the form, say, sum of AK, characteristic of rectangle K, K from 1 to big N, with AK being rational, and the rectangle RK being the product of intervals, say, little AK, not AK, but might be CK, BK, RK being product of a rectangle, say CI, K, let's put K here, K, I from 1 to D, because you're RD, where CIK and DIK are also rational. So, rational coefficients and the rectangle with rational coordinates. So these are dense here, these are dense here. Are we cool? Good. Good. So these spaces are separable. And this goes for 1 as well, right? So all these things hold for L1 as well. Now, as a matter of fact, so since we already are very close to close this discussion on separability, we may as well prove, so let me put proposition here. So this is essentially a proposition. Let's call this proposition 2. These spaces are separable. Proposition 3, L infinity of, say, RD, or if you want the space literal L infinity of sequences, is not separable. So let's do this. Okay. How do I show that this is not separable? We have seen that if I am on L infinity, then simple functions are no longer dense, right? Step function is no longer dense. So this means that this proof does not work. Okay? So remember, a simple function was just a finite linear combination of characteristic functions of sets of finite measure. Okay, that's what a simple function is. This is not dense in L infinity, because in L infinity you can take a function which goes, say, f of x equals to 1, and the real line is a function that's in L infinity, but you can never approximate it by a simple function. So this argument doesn't work. But this...
What if R is of finite measure?
What if your space is of finite measure, right? But even that doesn't work, and the same proof that I'm going to show you here applies. So L infinity of RD, or any subset of RD, is not separable. Well, okay, so let's just unless it's I'm going to say it's not separable if you are, say, generally speaking, L infinity of omega. It's not separable unless it is finite dimension, okay? But yeah, let's not go into that. Let's just keep this. You'll see what the idea of the proof is, and you will adjust the proof to whatever space you have in mind. But L infinity of any subdomain here, L infinity of any subdomain, say, omega containing RD is also acceptable. Unless it's just a finite number of points, and the measure is the counting measure, but then this would be a finite dimensional space. I don't want to avoid this basic case, but in general,
on compact set, maybe it's on compact if we take omega is compact also. This is it's same as a continuous function set or not?
L infinity of a compact set? No. I mean, if you take L infinity of 0, 1, no. Okay, so if you take just a discrete set of points, so L infinity of any subdomain of RD, some domain of anything of non-empty interior, then if something of non-empty interior, then it's not separable. Yeah, I don't want to go too much into the details of this. But so the idea to prove something like this is just, as I told you, this proof does not work, but this doesn't mean that there's no countable and dense subset. It could still be something different, but that there could still be some dense and countable subset of this guys. But the idea for you to do this is somehow so an idea to disprove the fact that it's separable, to prove that it's not separable, is if you have an uncountable collection of open sets, say OI, I belong to a certain set of indices I. So if you have an uncountable collection of open sets I, such that an uncountable collection of, say, of disjoint open sets. Okay? So if you have this, right, and so suppose you have this. Suppose your set, say, on infinity, or your set, the set that you have this uncountable collection of these open sets. Suppose that your set was countable, was separable. Your space, right? Your space E. Right, to have an uncountable collection of disjoint sets containing E. So suppose E was separable. This would mean that they have a dense collection of subsets, a dense and countable collection of points, right? But then each OI would contain a point. Suppose your space E was separable, and there will be, say, a countable collection of x1, x2, blah, blah. This would be dense on E. So each OI would contain a certain point. And you would just pick a point on the set OI. So this is your OI, There will be one point here, x, let's call it, and a guy. Okay, so you'd be making a set, a map N, that for each I, this family of indexes, associates some guy in the natural numbers, some indexes, okay, which is a map which is injective, because the sets OI are disjoint. Okay, so if you have your set OI here and the set OJ here, the choice of X and I that is inside here is certainly going to be the set, not the same as the set, the choice of X and J that is contained in here. So you find yourself with a map and that for each open set chooses a guy that lies inside, that exists because you're assuming it's dense. Okay, but this map that you constructed is injective. And you cannot have an injective map from an accountable set into the natural numbers. Okay, so this is your contradiction. Okay, so if you have such an uncountable collection of disjoint sets, then your space is not separable. Now, so when you're working with an infinity, if you're, so for example, if you're in an infinity of RD, or in an infinity of any subdomain of RD that has non-empty interior, you could consider, say, the functions, let's say the functions, characteristic function of the ball BR, which means this is just the, so you let, say, BR be in the ball, say, X in RD. Well, this is the ball. Close the open, doesn't matter. BR is just the ball centered in the origin with radius R. So you consider the characteristic function of this ball, BR. And what you do is you actually consider the open set, let's call it OR, of the functions f in L infinity of, say, RD, such that the L infinity norm of f minus characteristic function of BR is, say, less than half. Okay? So it's just this. So you have your inner infinity, you have this small VR. This is the characteristic function. It's a perfectly well-defined function in L infinity. You take the open set as the other functions in the space whose distance to this function is less than half. Okay? And I claim to you that OR intersection OS for different radii, R and S, is always empty. If R is different from S. And the way you see this, in fact, you just have to see that the characteristic function of the ball of radius R, the distance to the characteristic function of the ball of radius S in an infinity, how much is it?
1.
It's 1. It doesn't matter which ball is, one of the balls is smaller than the other, so their distance in an infinity is 1. So there's no way for a function to have distance less than a half from one and less than a half from the other one, because this would violate the triangle inequality. So there's no function in the intersection. And since R is a parameter that can vary continuously with the real numbers, this is an uncountable family of open sets that you wanted for here, for example. So if you are with some sort of subdomain of RD that has just a little non-empty interior, you can apply this argument, okay? Good. Therefore, this implies also by the previous observation, an infinity of RD is not separable. Good. How about little L infinity? How about, say, little L infinity. As I told you, I wanted also to consider these spaces of sequences. So this is the space of sequences x to be x1, x2, blah, 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 where, say, the normal infinity of x is just the soup of the normal xi's is finite. This space of bounded sequences is also not separable. Let's try to construct our open sets like we did here. So what would be a nice construction now of open sets?
Sequence of zeros and ones.
Just sequences of zeros and ones. So what you do is you take any subset A contained in the natural numbers. You take any subset A contained in the natural numbers, and you construct the sequence, say, XA, which is just like zeros and ones and zeros and ones, with ones in the positions of A. So if you take any subset of the natural numbers, you let the element XA to just have ones in the position of the set A. Right? And you do it again in the set and define, say, OA to be thus the sets of sequences x in L infinity such that the distance from x to XA is less than half. Same idea. So this is OA intersection OB for another subset is empty if A is different from B. And the reason for this, because you have that the distance from the element XA to the element XB is 1, right? So if A and B are different sets, so the element XA and XB must differ in one position at least, and so therefore this distance will be 1. So the set OA and OB cannot have a common element because this would violate the triangle inequality. Okay, so this is a family of disjoint open sets, and it's obviously uncountable because the cardinality of this family is the total number of subsets of the rational numbers, which we know it's uncountable. Okay? Good. So, I think this is a good point to finish the class today. Let's finish here. And next class, so this ends the discussion of separability. I just want to talk a little bit about, I don't want to go into the separability of LP or L infinity of more complicated measure space. I just wanted to discuss the case of RD, subdomains of RD, and the little spaces of sequences. But we're going to come back to the discussion on the dual and the reflexive properties. So today we show that LP for P between 1 and infinity is reflexive, and the dual is LP prime. We're going to show that L1 and L infinity are not reflexive. The dual of L1 is L infinity, but the dual of L infinity is something that is strictly bigger than L1. So this is what we're going to do for the class on Friday. All right, everyone. So we continue next Friday at 4. Thank you very much for your attention today.